In the last video, we went over how to compute the Clebsch-Gordan coefficients. In this video, we'll actually do a computation for a specific example. The example we're going to cover is the 1 by 1, that is S1 equals 1 and S2 equals 1. So suppose we have S1 is equal to S2 is equal to 1. The top state, that is the one with the highest value of S, is S equals 2. And if M is equal to S, that means that M is equal to 2 as well. And we can express that as a product state of the M1 equals 1 and M2 equals 1. And here in the green, we have S is equal to 2 and M is equal to 2. So this is a simple product state. The next lower state, where S equals 2 and M equals 1, can be obtained, and I'm going to leave the H bar off just to simplify things when I calculate the expectation values. So I'm going to drop off the H bar. So S minus, we're going to apply the lowering operator to the state S equals 2, M equals 2. And on the right side, that lowering operator is S1 minus and S2 minus, plus S2 minus applied to the state M1 equals 1 and M2 equals 1. Well, we know how to do that. We know that apart from the H bars, this is going to be equal to S times S plus 1 minus M times M minus 1, because we're lowering. And then it gives you the new state, S equals 2, M equals 1. Right? So this coefficient is exactly the same coefficient we talked about the last time when we derived the last one of the earlier videos. On the right side, we're going to have two terms. The first term is when we lower M1. And when you lower M1, you're going to get 0. So then you have the state 0 for M1 and 1 for M2. But in addition, you have this coefficient out here, which is, we should have been S1, which is 1, times S1 plus 1, minus M1, the previous version of M1, times M1 minus 1. And then when you lower the second term with S2 minus, you get a second term that looks similar, which is coefficient of 1 times, this is S2 times S2 plus 1, minus M2 times M2 minus 1. And now the state is M1 equals 1 and M2 equals 0. So you see it's a combination state of mixed product states. Each of these is a product state, and they mix, and M1 plus M2 is equal to M. That's always the case. Well, when I put these all together, I can solve for the 2, 1 eigenfunction. So 2, 1, when I put these together here, I get this is going to be 4 under the square root, so it's square root of 4 times 2, 1, the state 2, 1, plus this term is 0, so this term is 2, so square root of 2 times the 0, 1 state, plus square root of 2 times the 1, 0 state. Therefore, the state 2, 1, S equals 2, M equals 1, is 1 over the square root of 2 times the product state M1 equals 0 and M2 equals 1, plus 1 over the square root of 2 times the product state where M1 is equal to 1 and M2 is equal to 0. Which is not surprising. This is the symmetric state. You start with a symmetric state, you keep a symmetric state where you have the plus sign. And you get a 1 over the square root of 2 to normalize. Each of these is normalized independently. When you combine them, you have to use a 1 over the square root of 2 for normalization. So the Clebsch-Gordan coefficients then are both 1 over the square root of 2 for each of these two terms. Now we're going to obtain the 2, 0 state where s equals 2 and m equals 0. We're going to do that the same way. We're going to apply the lowering operator to s equals 2, m equals 1. And now the individual lowering operators are the sum of the two lowering operators to the state we just obtained, the S21 state, which is the combination state of 0, 1 plus 1, 0, all times square root 1 over the square root of 2. Again, over here we have 2 times 2 plus 1 for s minus 1 times 1 minus 1. That gives us a 0, so we're going to get a square root of 4 under here. Pardon me, a square root of 6 here. And then over on the right side, we have 1 over the square root of 2 times the quantity. And here we're applying s1 minus, so we're going to lower this. We get 1 times s1 is 1, and then 1 plus 1. And then here we have a bunch of zeros. And we get the state m1 is minus 1 and m2 is 1. We get a second term then, where we have S1 applied to this state, and now we get 1 times 1 plus 1 minus 1 times 1 minus 1, and now we lower this guy to 0 as well as this one remaining 0. We get a third term when we apply S2 minus to this, and we get a 0, 0 product function with the coefficient 1 times 1 plus 1 minus 1 times 1 minus 1. And then finally we get a fourth term rather, where we apply S2 minus to this term, and we're going to get a product state 1 and minus 1 for S1 and M1 and M2, and then 1 times 1 plus 1 minus 0 times 0 minus 1. This gives me the square root of 6, and then I have on the right side 1 over the square root of 2 times square root of 2 times the state minus 1, 1. 2 times the square root of 2 times the state 0, 0, because there's two identical terms. And then square root of 2 times the state 1 minus 1. And so when we now multiply this through, that cancels the square root of 2 in all cases. We divide by square root of 6, and we get the state 2, 0 for s and m is equal to 1 over the square root of 6 times the state 1 minus 1, 1, plus square root of 2/3, state 0, 0, plus square root of 1/6, state m1 is equal to 1, and m2 is equal to minus 1. So we can generate the other two eigenvectors for s equals 2 in the same way, because now we're at m equals 0, we have to go to m equals minus 1 and m equals minus 2. And they become this. So the state 2 minus 1 is equal to 1 over the square root of 2 times this. m1 is equal to 0, m2 is equal to minus 1, plus 1 over the square root of 2, m1 is equal to minus 1, m2 is equal to 0. And then the final state where you have s equals 2 and m equals minus 2 is the state where both m1 and m2 are minus 1. It's a product state, and the Clebsch-Gordan coefficient is just 1 here. And here it's 2. It's 1 over the square root of 2 in both cases. So that takes care of all the states with s equals 2. And there are 5 of those. Now, the remaining eigenvectors must be orthogonal combinations of the ones already generated, because they're all eigenfunctions. The eigenfunctions are orthogonal to each other. So we have to take advantage of that to calculate what's going on. So let's start with the state s equals 1, m equals 1. That's the next lowest value of s and the highest possible value of m for that. So that state, 1, 1, must be orthogonal to the state 2, 1. And if you remember, the state 2, 1 had 1 over the square root of 2 times 0, 1, plus 1 over the square root of 2 times 1, 0. And this state is clearly orthogonal to that. It's the orthogonal combination of the same two states with the same weighting. And you can imagine that you need to use those because they're the only two states which give you m equals 1 when you sum m1 plus m2. So this must be the state for 1, 1. We can apply the lowering operator just like before to get the state 1, 0. S minus applied to 1, 1. And then S1 minus plus S2 minus applied to this state 1 over the square root of 2, 0, 1 minus 1, 0. And we're going to get 4 terms again. So we get the first term here is 1 times 1 plus 1 minus 1 times 1 minus 1. That will be square root of 2. Then you have, on the right side, we have 1 over the square root of 2 times 1 times 1 plus 1 minus 0 times 1, 0 minus 1. That's for this term. And then you lower the 0 to a minus 1, 1. You then apply S1 minus to this term. You get the state 0, 0 with a, and there's a minus sign here, so it's minus square root of 1 times 1 plus 1 minus 1 times 1 minus 1 and state 0, 0. Then you get plus square root of 1 times 1 plus 1 minus 1 times 1 minus 1 state 0, 0 again, and now you have plus and minus in these two. And then you get a final state where you have minus square root of 1 times 1 plus 1 minus 0 times 0 minus 1, and the state is 1 minus 1 is multiplied times that. We can then realize this is square root of 2 times the state 1, s equals 1, m equals 0. And then you have on the right side 1 over the square root of 2 times square root of 2 times the state minus 1, 1. That's this term. These two cancel. And you're left with this one, which is square root of 2 with a minus sign times the state 1 minus 1. And so that is the state with s equals 1 and m equals 0. And you note that m1 plus m2 is equal to 0 in this case. So that state then is equal to the 1, 0 state is equal to 1 over the square root of 2 times minus 1, 1 minus 1 over the square root of 2 times the state 1 minus 1. We now do a further lowering, and we can get the state 1 minus 1, which must be orthogonal to the state 2 minus 1. And it turns out it's the same thing. You have a minus sign instead. So you have 1 over the square root of 2 minus 1, 0 minus square root of 1 over 2, state 0 minus 1. So we got 5 states for the s equals 2. We got 3 states for s equals 1. That's 8 states. We started with 9 states, 9 possible product states, right? Because each m1 and m2 can be 0, minus 1, or plus 1. And if we take all the possible combinations, that gives us 9 possible states. Out of those 9 states, we generated 8 states with values s and m. S equals 2 and s equals 1. We had 5 for s equals 2 and 3 for s equals 1. We have one more state, and remember that the values of s can range from s1 plus s2 to the absolute value of s1 minus s2. In this case, s1 and s2 are equal, so that means that s ranges from 2 to 0. And so we're missing the state with s equals 0. And that must be the linear combination of the 3 states that give you m1 plus m2 equal to 0. And it must be orthogonal to the other 2 states. And remember, so A, B, and C are chosen to ensure that the state 0, 0, it's orthogonal to the other states with m equals 0, that is the 2, 0 and the 1, 0 state. Well, if you remember, the 2, 0 state looks like this. Square root of 1, 6 times minus 1, 1 plus square root of 2 thirds 0, 0 plus square root of 1/6, 1 minus 1. And the state with 1, 0 is missing this term in here, but it has square root of 1/2 minus 1, 1 minus square root of 1/2, 1 minus 1. And so we have to make sure that this state is orthogonal to both of these states, and that will give us the values for A, B, and C. Now, just looking at this, it's possible to guess, but let's just do the computation. We do that by taking the inner product of 2, 0, and 0, 0. And that must equal 0 if they're to be orthogonal. And when we take the inner product, we get A times 1/6, square root of 1/6, plus B times the square root of 4/6, which is 2/3, plus C times the square root of 1/6. And so this is one equation. The next equation is making sure that this new state that we have to find is orthogonal to the 1, 0 state. In that case, we again take the inner product. We get A times the square root of 1/2 minus C times the square root of 1/2. These two equations plus the normalization condition should give us our final relationships. Well, if you look at the relationship here, this is, if you divide by 1/6 everywhere, with square root of 1/6 everywhere, you get A plus 2B plus C. And here you just get A minus C. So this tells you that A is equal to C because they add up to 0, or they subtract to 0. But then when you put A and C equal in here, you get 2A plus 2B equals 0, which means that B is minus A. So A is equal to minus B is equal to C. So we can write that the 0, 0 state is equal to square root of 1/3 times minus 1, 1 minus square root of 1/3 times state 0, 0 plus square root of 1/3 times the state 1 minus 1. Now, why do I have 1/3? Because the probabilities have to add up to 1, and they're all equal in magnitude. And so that means 1 over the square root of 3 is the proper coefficient to make sure that 1/3 plus 1/3 plus 1/3 adds up to 1. If we look at the table, this is the table we just generated. It's the 1 by 1 table. The top state is M1 equals plus 1, M2 equals plus 1. That gives you S equals 2, M equals 2. And there's a lone state there. You then have the second state down, which is a 2, 1, which is the positive combination of the state where M1 equals, the positive combination here, where M1 equals 1 and M2 equals 0, and the state where M2 equals 0, M1 equals 0, and M2 equals 1. Then you have the next one down, which has the coefficients as we had. They're all positive, 1/6, 2/3, and 1/6. The next term down that has the coefficients 1/2, 1 over the square root of 2, 1 over the square root of 2. And finally, the last one that has a product state of both M1 and M2 equals minus 1. And you can see that the other states are exactly the same as well.